Something to drive?
How?
Oh,
How
she
is this
thinks she
possible?
bought an
Is this
M.2.
not gonna work? Did I buy the wrong SSD? It'll force it in. No, I don't want to break it.
Oh no.
I just want to know what I need to do. One into your SSD and the other into your motherboard.
Why is she not watching Linus Tech Tips? Come on! We have a video on how to install an AMD cooler, for example.
I kind of hate this. Doesn't this look tacky?
But it's not supposed to be there like that.
This spot right here looks like it fits a power supply unit.
Wait, did she just decide we're gonna put the power supply in the 5 1/4 inch base? What is even happening?
I'm wrong. It doesn't go here, it goes here. Because this needs to be facing outwards, and this doesn't allow that, which means it go this way.
Ah, yes.
Assuming that we want to blow this part, I would want it facing out,
Oh no, now she's overthinking it.
but then that would make this upside down. I'm going with my gut and saying the fan needs to be facing towards and not downwards. Because most of the airflow is going this way.
Either way is honestly.
Yeah, this is right. Is it bad to plug in things into the wrong
Yes.
places?
Yes, it is.
Am I gonna destroy this computer by accident?
Maybe.
I think
Oh shoot, no.
this matches that one. So I'm gonna try.
The scariest part of this is that you can actually get it in there. I proved that when I did my blindfolded build. They should have just done a 10-pin PCI Express connector just to not have this happen.
After examining, it's wrong. But this one maybe.
Nice.
Let's try it. So this one says power LED plus, and this one says power LED minus. And I can see here that this says plus PLED and minus PLED. So I'm gonna assume from that the plus one goes here, and the minus one goes here.
GG, Sarah. Damn. Oh, stop wiggling things.
Hey, it didn't really click, but it's in.
Well, why don't you check and see if it's in by shaking the computer and seeing if it falls out? But no, don't.
Oh, this cable, probably I should move that. Yeah, I should move that.
Oh!
The fact that it was that easy to pull out maybe doesn't mean it was in properly. Oh, gosh.
Stop.
Oh, okay, that was a good snap, not a bad snap. You can never really tell. It's in. It's in! I have successfully installed the GPU. I guess we don't know that until
Success
we get
is
the computer
not
running,
the
but
right word.
let's just guess. So, I have kind of realized this cable is in the way, and I could remove the graphics card to kind of slide it down the back
No,
here,
please don't.
but I'm trying to decide if it's worth the hassle for me. Because the last time I tried to remove a GPU, it really didn't turn out for literally anybody involved in that.
I know that.
Oh! Stop!
But I really want. They like push it up.
Don't do that.
I think if I just push this.
Okay, she found the clip.
Okay, it made a click. Now pull.
Oh, that's, yes.
Wow, I did that so smoothly.
Yeah, wow, so smoothly.
Why wasn't it that easy the first time?
So smoothly.
Okay, wait. We're gonna go back now and do this.
Okay.
And this is lined up.
Please just push it in straight.
Now push.
Oh.
There we go.
Stop!
It's in. I'm gonna see what I can do about
there's
this
our
real quick.
SSD, still just hanging there.
I have no clue what to do with this SSD.
Manual!
Duct tape.
Duct tape.
I'm grabbing duct tape. Duct tape fixes everything.
Could you
Yeah,
have at
there
least
we
used
go.
double-sided
I don't want
tape
that to be visible.
so I can't see it.
I realized I have this little plate thing that's supposed to go
Oh,
here.
crap. I was so
I'm gonna try to
busy
get it in now
cringing out my
and
face
see if that works.
that I didn't even
I'm
know.
gonna get more with them themselves. Anyways. Hey everybody, welcome back to another video on networking and threads. I recently did a video on threads and sockets and trying to use threads in a multi-threaded server to try to improve performance a bit. If you missed that one, you may want to watch it first. I put a link in the description. So in that example, we were looking at a pretty simple approach. Basically, we have a server that accepts connections, clients give it a file name, and the server reads the file and sends its contents back to the client. It's not particularly secure because it allows a malicious client to read just about any file on your machine, so you probably don't want to run this on a publicly available server. I wouldn't. But anyway, this server is pretty simple, but it has some issues, and we're going to try to address those today. The main issue is that if we have a flood of thousands of connections come in, then our server is going to create a new thread for each of those connections, and that's going to use a lot of memory, and that could cause my server's performance to grind to a really sad, slow crawl, and that's definitely not what we want. So today I wanted to show you how we could upgrade this code in order to guarantee that we don't get into that specific situation. That is where we create an unbounded number of threads that end up degrading performance. And we're going to do that today by using a thread pool. Now, the idea with a thread pool is simple. Rather than creating a new thread for each connection that comes in, what we're going to do is we're going to have a set of threads we create at the beginning, and they're just going to hang out. They're going to be there available, and as work comes in, we hand them to one of the threads. And if there's no threads available, then that work just waits until there is a thread available. And this allows us still to work on multiple things at once, but it ensures that we don't create an unbounded number of threads. We pick how many threads we have, and we're going to stick to that number of threads. So in our code here, let's first define the number of threads we want to have in our thread pool, and I'm going to use 20, but that's completely arbitrary. The right number really depends on your hardware, how much memory you can afford to give this server, and the workload that the server is going to see. Now in your specific case, you probably want to experiment, play around with different numbers of threads, and just see how it affects performance. But for my purposes, 20 is going to work just fine.
So I had it from yesterday. True. Popular. Two. Okay. What do you call this?
And I'm going to declare an array of pthread. Hey everybody, it's really time that we talk about 53 days in Africa, no wrote basically the fact that packets of data coming in is just going to look like a stream of data. And we're listening on this server port, which happens to be set to 8989, but it can be any available port that your operating system lets you access. The check function is an error handling function that I wrote. Basically, it just takes advantage of the fact that
Okay.
a lot. I made a single function. Handle connection function is fairly straightforward. For this example, my server allows clients to read files from the server. The client sends the file name, and the server will then read the file and send the content. The client sends the file name, and the server will then read the file and send the contents back to the client. And this is actually really similar to how a web server works, but without the extra HTTP parsing, and it does have one big security. Server works, but without the extra HTTP back to the client. And this is actually really similar to how a web server works, but without the extra HTTP server, the client sends the file name, and the server will then read the file and send the contents back to the client. And this is actually really similar to how a web server works, but without the extra HTTP parsing, and it does have one big security problem, and that is that in its current form, this code just allows the client to read any file from your hard drive, so do be careful. This is an example, it's an effective example to show you how stuff works, but it's not meant to be used out in the wild on the big bad internet. Running this code on a publicly available server could get you into trouble. Okay, so handle connection reads whatever the client sends it up to buff size, and until we get a new line character, and we check for errors, and we null terminate the buffer. Okay, then I'm gonna print out the request just so we can see big web server works, but without the extra HTTP parsing. And it does have one big security problem, and that is that in its current form, this code just allows the client to read any file from your hard drive, so do be careful. This is an example, it's an effective example to show you how stuff works, but it's not meant to be used out in the wild on the big bad internet. Running this code on a publicly available server could get you into trouble. Okay, so handle connection reads whatever the client sends it up to buff size, and until we get a new line character, and we check for errors, and we null terminate the buffer. Okay, then we get a new. So handle connection reads whatever the client sends it up to buff size, and until we get a new line character, and we check for errors, and we null terminate the buffer. Okay, then I'm gonna print out the request just so we can see what's going on. Okay, so I check to make sure that the path is a valid file path using RealPath. Yes, I also have a video about RealPath. If you want more information there, I'll put a link in the description. Then we open the requested file, we read its contents out, and we send it back to the client. So we close the socket, we close the file, and then that connection is basically finished. We're done with that, so then we go back and we just wait for another. And we do this forever. This server just keeps accepting connections and handling connections over and over again. It accepts a new connection, it handles that connection, then it accepts another. And that's just what it does until we use Control-C to kill it. Okay, so to show you that it works, I made a quick Ruby script to be my client. This script connects to port 8989, that's the port that my server is listening on. It requests a file name. And we're going to have it request a particular file from my computer. I've also made a make file that compiles my server. Okay, so we can compile the server and we run it, and now we can see it prints out that it's waiting. Okay, so then in another terminal window, notice that I've set up some test files in /temp. They're all just copies of the server source code, but they could be anything. And so our client script is going to request one of these files. And we can run it, and it's going to grab the file and print it out. So we see that this works. But what I really want to talk about today is performance. If I were writing a real server that needed to handle many, many connections, it is really going to matter a lot to me how my server behaves when there is a lot of traffic coming in all at once. Okay, so let's look at how my little server behaves when we have multiple connections coming in at once. Okay, so first off, let's just time my client script, and I'm going to pipe the output to dev null because printing stuff to the terminal takes time, and I really don't want to time that. I just
Okay, let's go. Well.
I want to thank everyone for joining us to celebrate the proudest moment.
Want to time the interactions with the server. Also note that I'm connecting to the server on the same machine, because that's easy for me to test right now, but if we were connecting over the network, then there would be longer delays. At least I would expect there to be longer delays, and your results may be different than mine, depending on your network connection and your network setup. Okay, so now I want to look at what happens if I provide a bunch of connections all at once. To do this, I've made a shell script that basically just runs my little client script 50 times at the same time in separate processes. So they're basically just all hitting the server at roughly the same time. They're not going to be exactly the same time, but close enough. They're not going to wait until the previous one is completed. They're just all going to try to connect more or less at the same time, which is the case that we're interested in. It's basically simulating high traffic. And if I run it, we see some interesting things. First, you'll notice that several of my connections failed. Okay, to understand this, we got to look back at the code to see what's going on. Now, remember when I called listen, I specified a backlog. Now, this is the number of connections that the system will queue up before it starts rejecting connections. I started it back with a backlog of 1, but let's go ahead and change this to 100 because that backlog was the problem. A backlog of 1 basically meant that when I had all these connections come in, it wouldn't queue them all up. Now with a backlog of 100, we can now allow 100 waiting connections, and if waiting we run it again, you can see that now it works. And it's not really surprising, but 50 connections does take quite a bit longer than a single connection. But can we make things faster? The answer is probably. Maybe. But it depends a lot on how the server is spending its time. If the network connection is slow and the server is spending all of its time getting data to and from the client, then we probably can't. It's not without fixing our connection, because we're not really waiting on the server, we're waiting on the network. But let's say that we're waiting on the server, and the server is spending a lot of time handling connections. This is a reasonable server is waiting on the network, but let's say that we're waiting on the server, and the server is spending a lot of time handling connections. This is a reasonable assumption because disk accesses tend to be slow compared to processing. Now, if the server is spending a lot of time on disk accesses or on tasks that can be done on different processor cores, then maybe we can speed things up by handling connections in separate threads. Okay, so let's turn our server into a multi-threaded server. Now, there are different ways that we could use threads in our server. I'm going to start out with the simplest and then follow up with some more complicated options in a future video. For today, where we are going to use threads is down here in this code that handles connections. I'm going to change this so that it handles connections in separate threads, so each connection will be in its own thread. And then, if connection handling can actually be done in parallel, we might get some speed up. So first, I need include pthread.h. This gives me access to all those nice pthreads functions that we're going to use to create threads. Then we come down here where we call handle connection. And let's create a new pthread underscore t variable. That's going to keep track of our thread for us. Then we need to include pthread.h. This gives me access to all those nice pthreads functions that we're going to use to create threads. Then we come down here where we call handle connection, and let's create a new pthread underscore t variable. That's going to keep track of our thread for us. Then we call pthread create, passing in the address of that variable, and we need to provide a thread function and an argument address, like we always do when we create a new pthread. For our thread function, let's just pass in handle connection, since that's what we want the new thread to do. For the argument, I would like to pass in a client socket, but it needs to be a pointer, because that's how pthreads works, and preferably a pointer that isn't going to be messed with by any other thread. So let's allocate some space on the heap for an int, and we'll store the value of client socket right there. We can then pass in this pclient pointer as an argument to the thread. So now we're passing the socket effectively to the thread argument. Then we need to come down and change our handle connection function, because thread functions need to return a void pointer, and they need to accept a pointer. Let's rename the argument to remind us that it's a pointer now, not an int. Then copy it to a local variable once the function starts. And I'm going to free a pointer right here because we don't need it anymore, and I just really don't want to forget to do it later on. This isn't the only way to do things, but it's what I'm going to do right now. And then let's return null everywhere that we called return before to appease the compiler, since now our function is supposed to return a pointer. And then we need to come back up top and fix the function prototype so that it matches. Okay, now let's come down and make it, and that warning's going to bug me. I know it's just a warning, but let's fix it. Basically what it's saying here is that my thread function accepts an int pointer, and pthread create expects a thread function that accepts a void pointer. And really, a pointer is a pointer, and so from pthread create's perspective, this really shouldn't matter at all, but that's okay. I'm going to fix pthread. So let's come down and change handle connection to accept a void pointer instead, and then we'll just pass it to an int pointer, because that's what it really should be, and now we should be fine. Okay, and we got to change it up top as well. Then we run make, and now it compiles just fine, and it runs. Okay, so far so good. And now we can make a few requests. Notice that the request times are pretty similar to what we were seeing before. And if we run our 50 clients at once, we notice it takes about the same amount of time as before, which is kind of a bummer. So the question is, did adding threads make any difference at all? Well, let's look into it. To do this, I'm going to make some changes to my client. Instead of printing out the file, I'm going to have it time how long it took to get the file, and then print that out. We know that it's getting the content successfully, but now we can print that.
seen that.
Really worried just about performance. And I'm going to change my higher traffic script to request each of the different test files round robin style. I'll show you why in a minute. And this will let us see how our server looks to each of our clients. Okay, so let's compile and run our server. Now, I said before that all of my test files were just copies of the server source code, and that wasn't quite true. There is one exception, and just to make things interesting, there is a test file number 6 that I put in here that is a bit larger, quite a bit larger than the others. So some requests are going to take a while longer than the others. And that's why I changed my test script. So now 1 out of every 6 requests is going to request the big file, so we can see how this is going to influence my server's behavior. Anyway, now we can test out a few single accesses. You can see that the short accesses are quick, and requesting number 6 takes longer, not surprising. And when we run all 50 at once, you can see this again. Some connections are very fast, and some take a lot longer, especially down here at the end. Some requests are taking more than a second to complete. So what happens if we don't start taking?
returns me pointer to the first integer in the one-dimensional array. So P0 returns pointer to integer. We will
We can just comment out pthread create and call the function directly. Now we're handling the connections sequentially. We compile it and run it, and single connections are taking about the same amount of time as they did before. But when we run 50 at once, we see something different. Notice how all of the connections are now taking about the same amount of time, and most of them are taking a lot longer than they did before. What's happening is that slow connect. Notice how all of the connections are now taking about the same amount of time, and most of them. Are taking a lot longer than they did before. What's happening is that slow connections are causing delays, and the other pending connections have to just wait their turn. They can't be processed until the one before them finishes. So with threads, the super fast requests finish quickly, and they got out of the way, right? Handling multiple requests. Currently slow down the big downloads a bit, but a lot of our clients got better service. And now just for clarity, I want to tweak one little thing and have my client print out which file it's accessing. So now we can see in our output which files are taking how much time. And now when we run it, you can see that with threads, the slow connections are mostly the long number 6 connections. But without threads, the long number 6 connections stall everybody that comes after them. Okay, so imagine if all threads did this. When you access YouTube, your YouTube video request would have to wait until everybody before you in line finished downloading their entire video. The server might still be able to serve up the same amount of video, but you, the client, could be waiting here for days before your video starts to play. The reality is that clients requesting large downloads are probably willing to tolerate a small slowdown. They may not like it, but they're downloading the special extended version of Lord of the Rings trilogy, and they know it's going to take a while. So what's going to be an extra 5 minutes of download time, especially when you can start watching the video before the whole thing is done, but an extra 10-second delay on your website's homepage could mean the difference between people using your site or people leaving your site and never coming back. Okay, so I'm almost out of time, but let's look at one last thing. Our server here is pretty fast. It's accessing a small set of files from a solid-state drive, so these requests are pretty fast and they're pretty uniform. But what if my server had to access a slower magnetic disk? Or had to access another server to handle the request? Or basically it has to do anything slow that doesn't tie up the processor. And for illustration purposes, I'm just going to come down to my code and I'm just going to add a 1-second sleep in our handle connection function. So this is my slow but not CPU-intensive task, and this is really where we are going to see major overall differences from using threads. Now, when we run our 50 concurrent connections, they all just stack up and things are super slow. It takes over 50 seconds to run all of them through. Each one waits for the one that arrived first to finish. But if we go back and use threads, now all of that waiting is done concurrently as well, and now we do save a ton of time, and all those accesses finish in just a few seconds. Okay, so just a few things. This is where I'm going to stop for the day, but I want to point out a few downsides to this approach. Yes, it's simple. When we have more work to do, we just spin up a new thread to handle it. But what happens if I have 10,000 connections all at once? What about a million connections? Each of these threads requires memory and CPU time, and at some point, more threads is not going to help. More threads is just going to start killing my performance, using up all my memory, and things are going to get really, really slow. The other thing is that we're creating a new thread for every connection, and creating new threads takes a little time. We can probably save some things. This is where I'm going to stop for the day, but I want to point out a few downsides to this approach. Yes, it's simple. When we have more work to do, we just spin up a new thread to handle it. But what happens if I have 10,000 connections all at once? What about a million connections? Each of these threads requires memory and CPU time, and at some point, more threads is not going to help. More threads is just going to start killing my performance, using up all my memory, and things are going to get really, really slow. The other thing is that we're creating a new thread for every connection, and creating new threads takes a little time. We can probably save some of that time by reusing the threads we create for future connections, and we'll talk about how to do that in a future video. Be sure to subscribe to the channel if you want to make sure you don't miss that video, and I'll see you soon. Bye.
Yeah, I didn't finish that.
Hey everybody, welcome back. Today we're going to talk about threads, one of the most interesting, one of the greatest, one of the scariest, and possibly dangerous programming tools you have at your Have you ever wondered how to make your program work on two things at the same time? Well, today we're going to learn how. Several months ago I made a video about fork and exec. I showed you how to use fork to create a new process, to basically clone one process into two processes. Hey everybody, welcome back to another video on networking and threads. I recently did a video on threads and sockets and trying to use threads in a multi-threaded server to try to improve the performance of it. If you missed that one, you may want to watch it first. I'll put a link in the description. So in that example, we were looking at a pretty simple approach. Basically, we have a server that accepts connections, clients give it a file name, and the server reads the file and sends its contents back to the file. It's not particularly secure because it allows a malicious client to read just about any file on your machine. So you probably don't want to run this on a publicly available server. I wouldn't. But anyway, this server is pretty simple, but it has some issues, and we're going to try to address those today. The main issue is that if we have a flood of thousands of connections come in, then our server is going to create a new thread for each of those connections. And that's going to use a lot of memory. And that could cause my server's performance to grind to a really sad, slow crawl, and that's definitely not what we want. So today I wanted to show you how we could upgrade this code in order to guarantee that we don't get into that specific situation. It is where we create an unbounded number of threads that end up degrading performance. And we're going to do that today by using a thread pool. Now the idea with a thread pool is simple. Rather than creating a new thread for each connection that comes in, what we're going to do is we're going to have a set of threads we create at the beginning, and they're just going to hang out. They're going to be there available, and as work comes in, we hand them to one of the threads. And if there's no threads available, then that work just waits until there is a thread available. This allows us still to work on multiple things at once, but it ensures that we don't create an unbounded number of threads. We pick how many threads we have, and we're going to stick to that number of threads. So in our code here, let's first define the number of threads we want to have in our thread pool, and I'm going to use 20, but that's completely arbitrary. The right number really depends on your hardware, how much memory you can afford to give the server, and the workload that the server is going to see. Now in your specific case, you probably want to experiment, play around with different numbers of threads, and see how it affects performance. But for my purposes, 20 is going to work just fine. And I'm going to declare an array of pthread_t's. This is going to be my pool of threads. And then at the start of our server, I'm going to create the threads. Now I'm going to go through and from 0 to the size of the pool minus 1, and I'm going to call pthread create for each of the threads, and I'm going to pass in a thread function, and I need to learn how to spell, and then we need to define a thread function, which is going to be a bit different than what our threads did before. Before, they just started, they handled the connection, and then they died. And now we're going to do things a little differently because we actually want to reuse those threads. Okay, so now let's go down and look at where we handle those connections. This code down here isn't going to do what we want anymore. So we really need to replace it with code that is going to hand off each new connection to a new thread, assuming that there's a thread available. But how do we do that? Basically, the short answer is we need to be able to put connection information somewhere where these threads can find them once they become available. So for this, we're going to need a data structure. Fortunately, recently we've been talking about data structures, specifically linked lists, so that's what I'm going to use. Now, if this is uncharted territory for you, please go watch my linked list videos and come back, this will all make more sense. I'll be sure to link to those videos in the description. Now, in this example, I'm going to use a special type of linked list called a queue, and a queue is just like any other linked list, except that we always add nodes to one end and we always remove nodes from the other end. So it's a first in, first out type data structure. That's really the only thing that's different. And we call adding a new node, we call enqueue, and removing a node from the end, we call dequeue. So enqueue adds a node to the queue, dequeue removes the first node from the list, from the queue, I should say. And in my implementation here, I'm going to have return null if the queue is empty and there's nothing to pull off the queue. So that allows us to see, hey, we just checked the queue and there's nothing to do here. Okay, so back into the main program, now I'm going to include my queue header file. Oh, and I need to also include prototypes for enqueue and dequeue in my header file. Then back in my main server code, when we get a new connection, let's just take that connection like we did before, but now we're going to add it to the queue. And there will stay until one of our threads comes along to grab it off. Okay, now let's define what those threads do. We never want these threads to all die, so we're just going to put them into an infinite loop. And you can also, of course, add some sort of termination condition here if you want, but for simplicity, I'm just going to leave it here with an infinite loop. When we control C, everything else will just die. Okay, so then each time through the loop, we're going to call dequeue, which will see if there is a node on the queue, and if there is, then pclient will not be null, and so in that case, we have work to do. Or I should say that thread has work to do. So now, the thread can just call handle connection, to handle the connection, just like we did before. And then when it's done, the thread is going to loop around again, check for more work on the queue, and if it finds it, it will keep handling those connections for more work. So it's going to keep doing this forever, over and over again. Okay, so now let's see if it works. So it doesn't quite yet. I forgot to use quotes in my analysis. That just tells the compiler to search the current directory as well as the standard directories that it searches for header files. And I also forgot to compile my queue code. That's definitely a problem. So back into the make file, let's add a rule to build.o files and a new one for building the server. A rule I need to add -c flag to the code rule. Okay, so now it compiles all the pieces for me. And I can run my server. Once again, just like in the last video, we were waiting for connections. Now if I run my script that fires off 50 clients at once, you're going to notice that it works and we get comparable performance to the original version which I explored in the last video. But I want to point something out. We also got lucky. This server still has a fairly major bug in it, and if I run it again, you're going to see a weird subway. Okay, so that's not pretty. What happened? The problem is simple. We have a shared data structure, our queue, and a queue isn't thread safe. So if two threads try to remove work from the same queue at the same time, or if one tries to dequeue while the main thread is calling enqueue, data structure can get in a bad state, leaving us with bad pointers or double freeze in here. Those of you that are new to the channel, this is called a race condition. I talked about those in my previous thread videos. And the fix is straightforward. All we need to do is protect those calls to enqueue and dequeue. And we're going to do that with a new text block. Now we can do this in myqueue.c, or I can also do it here in my main server code. In this example, I'm just going to do it in the main server code. That's really an arbitrary decision that depends on your application.